Hello everyone, this is Professor Ma, and this is the part on the triple integrals in cylindrical and spherical coordinates. So I assume you are familiar with the previous videos. That's which we part A, which we talk about the how what cylindrical and spherical coordinates are. So I'm going to pick up on where we're going to do triple integral over solids that can be described easier using cylindrical or spherical coordinates. Okay? And how do we convert integrals from x, y, z's into these and then set up iterate integrals in r theta z or rho theta d in the two systems into iterated integrals. Okay. Basically, goes like this. Well, for the cylindrical coordinates, what we do in triple integral, again, is we cut up the domain. The domain over here is a solid, okay? So it has three variables, r, theta, z. So we think what happened, we talk about a very small, minute amount of increment, dr, d theta, dz. So I increased all three of them a little bit. Okay, so when I go from r dr d theta, r dr is going to be from here to here. Okay, the r increase from this is the amount of dr. D theta is the amount of angle change, these little slivers. Okay, and we had from polar coordinates, they tell us that the area, the dA of this polar area is roughly r times in differential forms, actually is dr d theta. That is how much you increase by the radius and how much angle you increase by. That depends on how far these pieces away from the origins, because as you go out, that piece gets bigger and bigger. So you have to account into the distance r, multiply the dr d theta to obtain the rough area of this little wedge, little piece of plane, a little wedge. Okay. Now I'm going to take the wedge, and this is the base of this. I'm going to let z change. Suppose now I let z increase a little bit, so basically it forms a little shape like this with the same base as before, and then the volume of this of the entire things, which is the dV, the differential, a small amount of volume, and that's going to be this r r d theta times how thick it is, dz. Okay, so this is the volume differentials in cylindrical coordinates. Okay. Now, suppose I have a function defined over a solid. The solids described with the cylindrical coordinates in these manners, and the integral like h be a, for instance, functions. That's the density at a point in the solid. Okay, I multiply by the little wedge cubicle, the volume of that, and that these entire things will be the mass, roughly, of that little chunk, wedge chunks of wedge. And I want to add up the mass of all these wedge chunks. And the one that further out, closer in, okay, they're all slightly different size, but I'm going to let d theta, d are all shrunk to zero. So eventually all the chunks, the volume of each chunk all go to zero. And so then I add them up, that's an integral. And this is the triple integral over in the cylindrical coordinates. Okay, so first let's describe a couple of solids. Okay, in order to do this, we're going to change these triple integrals into iterator form, I mean, dr d theta dz or whatever, depending on which one, or d rho d theta dz. We need to do iterator integrations. So here's the algebra for doing it. First, to use, for instance, cylindrical coordinates to do integrations, I need shapes that can be described by cylindrical coordinates easier, like for instance, long blocks of that chunks of a shell of cylindrical shell, a piece of a cylindrical shell, and this can be easily described. Okay. The base, again, cylindrical basically is polar equation. So first I describe the base. Okay, the theta go from pi over 6 up to pi over 3, and then the radius go from 5 to 7. And that's for the polar, the base. Then the z part, you just tack along whatever z goes from, in this case, is from 0 up to 3. So this will be the set description of this column, okay, wedge column, if you like. And here is a can with a lid floating in space. Okay, it's how do I know it's a can? Well, this equation, if I square both sides, I get z squared, move the x squared over, y squared over, I get that. Oh, that's a sphere of radius 5. So this is just a part of the sphere as the top of the can. So the circular base in polar is given by this, the angle theta 0 to 2 pi, the radius from 0 to 3, and that you tack along the z. The height of this can, the base is the circular base is floating at the z equal to 1. It goes up to the round sphere, z equal to root of, again, we see x squared plus y squared, so this is minus r squared. So we're looking for minus x squared minus y squared, or x squared plus y squared. So that changes to r squared in the cylindrical. So this is a description of this tank, oil tank, if you like. Okay, so here's how we set up the triple integrals. If we have the descriptions in this r theta or theta r, usually in the cylindrical form, it's easier. We start with theta angle, then the r inside and outside, the boundary, the polar curve. Okay, from r to what to what. So if the solid is described in this fashion, again, we set the integral starting from the outside. Okay, this is the integral in the middle portions. Then you do the second part of the dr, and then you have the innermost part, which is this part, the last part, which is dz. Okay. I mean, what's dz? Basically, this is the setup. Then this is the dv. That's what I'm saying. Okay. So for the last one, this is how we set it up. And if I integrate over 1, then rd, rdv, rd, zd, rd theta is the dv. Okay, so integrate over dv, you get the entire volume. And here's the calculations. I won't bore you with it. Okay. Here is the spherical coordinates. Okay. Again, we have 3 variables. And so what we're going to propose is what happens if I increase the rho, the distance from the center outward a little bit. Now I'm going to change the angle, increase the angle theta by a little bit. And now I'm going to change the pitch angle downward a little bit. When I do all three of them, it cuts up little chunks of the sphere. Okay. Here's the rho goes outside, and I want now say suppose I extend the rho a little bit by d rho, and I'm going to swing and let theta change by delta theta d theta, and then my tilt angle I'm going to change the tilt from here downward now to change plus delta v like that. When I do that, a little chunks of like these solid is created, and the question is, what is this volume? Roughly, this volume is in terms of this chunk is going to be, in terms of this increment. But notice this increments of how big this chunk is depends on how far you pitch. If you pitch very little, then this chunk is very small. If you pitch all the way, if you're talking about the chunks, in other words, think of a wedge of oranges. Okay. And here's the center, and I'm going to, from the center, I'm going to cut at angles, and I'm going to cut wedges out of these like this. So I'm going to cut like, and I'm going to change this angle phi again, and then I'm going to cut it through again. I'm going to cut it again like that, and so I'm going to, each time the angle I pitch is the same. And notice the pieces on the bottom, these pieces is really bigger, a lot bigger than the pieces of the other ones on top. It's very small, it's in the corner. The one on top is a little sliver, but the one on the bottom is like big slab on the floor. So in other words, this dV things of these little chunks depends very much on the pitch angle. The big chunks is when the pitch angle is close to pi over 2 down below. Okay. The small chunks you only get little when the pitch angle is close to 0, so it goes to 0. So this is, we get these formula coming out of spherical geometry, so I'm not going to prove these, but basically you can prove, therefore, I'm going to assume, therefore, this formula, that chunk depends on rho square and sine of the pitch angle. Okay. So when the angle is very small, like 0, then sine of that angle is almost 0. It's almost nothing. But when the angle you're pitching at is already close to 90 degrees, then sine 90 degrees 1. Then you're going to pick up a big chunk. That's what this differentials says. Okay, and so this is how we convert functions h in spherical coordinates into iterated integral, and using interpreting delta v as rho square sine phi and delta v delta theta. Okay. And then here's how we set up integrals. Appropriate limits of integration depends on how this volume is described. Again, the volume must be described in spherical coordinates. So here's some example. Okay. For sphere, and here's is the description of sphere. Rho's can be anything from 0 to r, and the pitch angle 0 to pi, and then the theta is false 360. Okay. And a spherical shell then is the rho is between one sphere and outer sphere. The rest is the same. And you have spherical wedges, okay, spherical cone. So we'll go through some of the. So you can go through look at some of the description of these solids to do with spheres. That's why it's called spherical coordinates. Okay, chunks of the sphere somehow. And we want to now talk about how we integrate over these shapes. Okay, so here everything is right now is in x in rectangular chunks x, y, z. Okay, so we want to convert everything to spherical coordinates. Okay, and so again, the sphere is the sphere of radius 1, and below is the this quadratic surface is cone shape. Okay, and in particular, I know what the pitch angle is because I can solve for the line, the slope of the line when I set x equal to 0. Okay, for instance, at 0, so I get this line, equation of this line is z is equal to root 3 over root 3 times y. Then you can say y. So the slope of this is square root 3. Okay, and then you can say, oh, I know what the angle is. That's pi over 6. Okay, so just a little trick there. And then now it's easy to describe this in spherical coordinates. Okay, rows between 0 up to outer sphere of radius 1. Okay, and theta is again 2 pi, 360 around. Then the pitch angle is only up to pi over 6. Okay, and now the integrand. I need to convert the integrand into rho theta phi. That's why we go back to the original conversion rule. The z is rho cosine phi. Okay, so go back to the conversion rule. Yeah. So and then put everything in triple integral. That's it. Okay, this is the dv part. The volume differentials. This is the conversion of the formula in rho theta phi in spherical coordinates. And this is the descriptions of the solid we're integrating over. This ice cream cone we're integrating. And that's what it comes out. Okay, I will leave this for you to check. And okay, so the ideas there for what we've been doing is in double, remind us, we've been doing this in double integral dx dy or dy dx, type 1, type 2. And well, basically we have to write things into iterated integrals, integrate y to x, y step by step. And in what we just went through in triple integral, the same thing. We're going to set up this dx, dy, dz, or maybe in cylindrical dr, d theta, dz, or in spherical d rho, d theta, dz. And after the conversions, they're just a bunch of symbols of integrations with a bunch of functions. And just the variable names are different, x, y, z, rho, theta, phi, blah, 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 blah. They're just different symbols. But when you get to that point, and then a couple of cases which you know is worth noticing. So when we're integrating something, so here x and y may be r and theta, okay? X, y, z might be rho, theta, phi. But if the integration come out to be, two functions, the integrand turn out to be two function multiplied, okay? Again, this could be r, this could be theta, this d r d theta, and this r, this is r, this theta, and stuff like that. If that's the case, okay, x y over here means nothing except just dummy variable. If the integrand looks like that, then notice that we can treat this as a constant, so the f of x can actually pull out over here. So these actually become the product of the x integral with respect to x times the y integral with respect to y. Okay. So these sometimes is convenience rules, and these things go to 3 dimensions too. Okay, suppose our triple integrals and the functions I'm integrating r theta phi turns out the product of 3 separate functions in each variable. Then I can actually take the triple integral into 3 parts, calculate each part and multiply the product. Okay, so and we can use that to calculate these functions. Okay. Put all the rows one side, put the sine phi and the theta. Okay, because the notice this is true for integrating over a box. Okay, again, this is oh notice this rule is always integrating over a box. A B C D, A B C D E F all. Okay, so for the other problem, we can do this last example. Okay, and that's it. Okay, bye bye.